Is that, hang on a second. Okay. All right. Okay, let me talk about the final exam. So I've posted this document, final exam topics. And so that will be 1 week from today. And it will be in class. And so this is what you can expect. So you will be allowed to have 2 sheets of notes, okay? Writing on the front or back. I will collect your note sheets with the exam. So, create your own and, put your name on them. And then I guess I should write, you'll need a calculator. But yeah, I guess that's assumed. And it'll be, in class pen and paper. All right. So one will be, so yeah, I guess these are a bunch of topics. I wrote possible topics. Yeah, but anyway, okay. Um, K nearest neighbors classifier. So I'm going to provide some training data with 2 classes, and it will basically be a list of their points and their labels. And then I will provide a test point, and you'll tell me the classification for different values of K. And there will be a graph and you can kind of plot them to kind of help. So it'll be a matter of you kind of figuring out which one's the closest neighbors and identifying them as such. Um, I'll have a question covering support vector machines, and this one is a little bit more of a um, I guess like a match. And so I will provide some pictures and they'll all have like the same data, but we'll have different kind of boundaries drawn. And what I will provide is I'll provide basically, yeah, pictures that look kind of like this with different boundaries, and then I'll also say, a command, and I'll say, was it linear kernel or was it Gaussian or radial kernel? So obviously straight lines will be linear, and then the curvy ones will have to be radial. And then I will say, and I'll have, different values for what the gamma was. So it might be SVM with radial function and cost 1 gamma 1 or cost 1 gamma 10 or cost 10 gamma 1 or just different kinds of combinations and you'll have to kind of match. So um I think probably the trickiest ones will be like is cost 1 with gamma 10 versus cost 10 and gamma 1 type of thing. And so um, you have an example in I think homework 4, um, where there's SVM boundaries drawn and with different values for cost and gamma on the radial basis. And I would say just kind of fiddle around with that and get a better feel for how different values of these parameters will draw different boundaries. Um, then I will ask you to do some k-means clustering, okay? And so I'll provide some unlabeled data, and this will be two-dimensional data, and I'll provide maybe some initial assignments, and then I'm going to ask you to do either 1 or 2 full iterations of k-means clustering. So that means you're going to calculate the centroids, and then update the assignments and then maybe recalculate the centroids and update the assignments based on that. So k-means clustering, it's this iterative algorithm, and so I'll ask you to do a couple iterations of that. Um, I'll also have a problem where you will apply a transformation function. And so for this, I'm going to have you do uh, k-means clustering with a kernel, but I will actually provide the transformation function. So I know, as I covered the topic, I said you don't actually need to do the transformation, but for this problem, um, I'll have you do the uh, actually apply the transformation. So I'll give you kind of basically a simple function that will transform from 2D to 3D. Otherwise, if it's, any higher dimensions, it just becomes too tedious. So a simple function, I'll provide just a few data points, okay, and maybe initial cluster assignments. You'll transform them. You'll calculate distances, centroids and distances in the transformed space in 3D, and then do some basically cluster them that way. Um, then I have a Bayes classifier problem. Okay, and in this one, I might give you a binomial or a normal distribution as far as the data that you're seeing. Okay. And then as far as the proportion prior goes, you'll just use kind of like the proportion in the training data. So if in the training data it's like uh, 75% class A and 25% class B in the training data, that's what you'll use for your prior cases. And and then I'll give you a test case with some kind of value. And based on that, I'm going to ask you to give me the probability that it's in class A or class B or something like that, right? So an example of like a normal PDF problem would be like you have um, these numeric measurements. And so I could say, we have the heights of 5 people, and you have two males at these heights and 3 females at this height. And I say, okay, if somebody comes in at 68 inches tall, what's this? And you would use like the sample mean and sample standard deviation to kind of estimate the PDFs of your things. Okay, so that's an example for normal PDF. An example for binomial would be something like kind of the marbles from the different factories. So I have like you've got um, different bags. 10 are from factory A, 5 from factory B, 5 from factory C. And then when you open them up, factory A is 10% blue, factory B is 20% blue, factory C is 30% blue. And then let's say you open up a bag, there's 20 pieces and 3 are blue, so that's 15% blue. And then based on that, give me, what's the probability that it's from factory A, B, or C. Okay. So these are some examples there regarding the Bayes classifier. Okay. In today's lecture, I will uh, go over the EM algorithm and principal components analysis. And so for the EM algorithm, I will provide, a small data set in one dimension to keep our calculations simple. It'll be like a normal distribution. And I'll say so, and the EM algorithm is iterative. And so I'll say, in the most recent iteration, the mean and standard deviation values for each cluster is something. So, for example, I might say cluster 1 has mean of 3 and standard deviation 2, and cluster 2 has a mean of 6 and standard deviation 2 or something. And based on these kind of uh, mean and standard deviation values, you'll kind of recalculate the weights similar to the Bayes classifier, and then based on that, you'll recalculate the means. I won't have you recalculate the standard deviations, but that's part of the EM algorithm, and I'll go over the EM algorithm in today's lecture, and then the other part will be principal components analysis. And I will provide a small matrix of data in 2 dimensions, and I'll ask you to find the first principal component. And then once you find the first principal component, you'll project the data down to that 1 dimension. Okay. And then there will be a handful of conceptual questions that span the course, and uh, that will be that. Okay. But these, as far as any kind of problems that require computations and stuff, this is what you can expect. Okay. Um, the there's homework 5. I will make due on the last day of class. I'll give you until Thursday, so basically 1 week from today, and it covers a bunch of these unsupervised learning, the clustering, and the EM algorithm in homework 5, and I assume you guys are working on that. So that will be due September 11th. I've also posted this this I guess assignment, but it's not an assignment. So in the regular quarter where you have 10 weeks, I assign 6 homework assignments. But in the summer quarter, we only have 6 weeks, and it felt like it was too much homework to give you to assign a 6 homework assignment. But anyway, this one covers principal components analysis, and I think and I've modified it just to kind of include some examples that are relevant for studying for the final exam. So I do recommend, taking a look at it and kind of working through it. Obviously, this thing, you're using the computer for PCA, okay? But on the exam, you'll want to do things by hand, okay? So, this uses um, but there's kind of a lot of stuff here, and I think it will be helpful to work through, um, if you have the time as you're studying to work through it as you prepare for the final exam. So that's there, but it's not due. So for summer, only 5 homework assignments, and then I've extended the deadline for homework 5 to our last day of class. Okay. Any questions, I guess, regarding the exam before I go on and jump into today's lecture? Yeah, we're good. Okay. All right. And then we'll take a look. So this lecture covers the EM algorithm. There's a bunch of slides that just are pictures, and then this one will cover PCA. All right, so we'll go ahead and uh, go through this. And then next week, so week 6, Monday, uh, I'll just kind of do, I don't know, like a fun stuff that I won't test you on. I want to make sure I cover kind of all of the basics now, so you have time to study and prepare for the final exam. And then week 6, Monday, or not Monday, Tuesday, I'll I don't know, I'll just cover some of the interesting things. I don't know that may or may not be directly related to other stuff in the class. There was some cool stuff that I saw at the R conference, and so maybe I'll show some of that. I don't know. But anyway, that's uh, if you skip week 6 Tuesday, you're not going to miss anything like critical or vital. Um, but anyway, that's that's what we have. All right. So let's talk about the EM algorithm. Okay. So the EM algorithm is stands for expectation maximization, and it can be used in situations where you both have missing data and unknown parameters. And I really like this video produced by Ritvik Matt's channel. He's a UCLA alum. And anyway, he's got a good explanatory video. And so I'm just copying some of his examples here. And so, in one basic scenario, let's say you have missing values, but you know everything else, right? So let's say you're given the values 1, 2, and some mystery value x, and we say, hey, these values are coming from a distribution. This distribution has mean 1 and standard deviation 1, right? So what is your best guess for the missing value of x? Okay. And our best guess here is basically going to be like the value with the highest likelihood or highest probability. And so that will be a value of 1 at the mean. Okay. Um, but obviously, the real value could be anything. But if you had to, what is your most probable guess, you would pick the value 1 because that's the mean of your distribution. Okay. Um, Here's another scenario. This time you have all of the values, but a parameter is missing. Okay. So you have the values 1, 2, and 0, and you're told they're coming from a distribution, but the mean of this distribution is unknown. Okay. So what is your best guess for mu in this case? All right. So now you're going to look at the data and you're going to say, okay, let's get the maximum likelihood estimate of the mean based on our data, and that's going to be the sample mean. So we would do, okay, 1, 2, and 0 divided by 3. The mean here is 1, and so we would plug that in for the mean here. So that would be what we would get here, okay? And um, and let's say we're in this situation where we both have missing values and a missing parameter. The parameter is unknown to us. Okay. So we have some data, the uh, numbers 1, 2, and missing value x. And we say, hey, these come from a distribution, but you know what? We don't know the mean of this distribution. Normal distribution with mean unknown value mu, standard deviation 1. All right. So what is our best guess for what x should be, and what is our best guess for what mu should be? Okay. And so now we're kind of in this situation where it's a little bit trickier. And this is where we can use the EM algorithm. And so one approach is to just kind of take this iterative approach. And you just start off with a guess for mu, and you kind of iterate back and forth. So if I'm just going to start off with an initial guess of 0 for our missing, our unknown parameter mu. And if I say, okay, I'm going to guess that the mean is 0, using that, I'm going to take that and make a guess for the missing value. And my best guess for the missing value in this case will be x is 0. Okay. So now filling 0 in for my missing value here, my data is now 1, 2, and 0. Okay. And based on this, what is my best guess for the unknown parameter mu? Okay. So now my guess at time 1 for mu is going to be 1. And now that I have that, um, I'm going to update what my guess for the missing value is. Okay. So my guess for X is going to be 1. And so now my data is 1, 2, and 1. And what do I guess for the missing value of mu, or the unknown parameter mu? 1.33. And I kind of iterate back and forth between updating um, our unknown parameter mu and updating our missing value. Okay. And so this is a very simple example. And if you iterate back and forth between updating your unknown parameter and updating your best guesses for the missing values, eventually you'll converge to filling in the missing value with 1.5 and the unknown parameter to be 1.5 as well. Okay, so we're going to take this idea of trying to figure out both the missing values and the unknown parameters in this iterative fashion, where we update our guesses for the unknown parameters, update our guesses for the missing values. And we're going to apply this to a mixture of Gaussians. Okay. So here I'm going to just start off by generating data from 3 multivariate normal distributions, or normal multivariate Gaussians. And our data generating process is going to look something like this. Okay, we're going to randomly select to either come from one of 3 clusters. Okay, and we'll say values come from cluster 1 with probability 0.5, cluster 2 with probability 0.3, and cluster 3 with probability 0.2. Okay, and then once you decide which cluster it's coming from, then you're going to generate a 2-dimensional point. Cluster 1 is centered at 0, 0, but and has variance 9009. Okay, so no covariance between x1 and x2, but kind of a lot of variance there. Component 2 is centered in the upper right corner at 4, comma 4, and it has this variance with high covariance between x1 and x2. Component 3, which accounts for 20% of our data, is centered in the lower left corner at -4, -4. And the variance of x1 and variance of x2 is 2. And then there's covariance, negative covariance between these two. And so when I generate my values, okay, I can use the computer here. The overall mixture model can be represented in this way. We could say the overall kind of probability of x given all of the parameters, okay, and the parameters consist of alpha, the mixing proportions, plus all of the different mu vectors and all of the different sigma matrices. Those are all gathered in this capital theta parameter. And what this is going to basically be is it's going to be the sum of our different PDFs. Okay, so we have the PDF of component one multiplied by the mixing proportion plus the PDF of component 2 multiplied by the mixing proportion plus the PDF of component 3 multiplied by the mixing proportion. Okay. And, we're going to have it for basically the entire, I guess, Euclidean plane of x1 and x2, right? So we're going to say, all right, what's the probability of getting a value at 0, 0? Okay. We say, all right, it's the sum of our three different mixture components. Okay, what about, the point -2, 2? It's going to be the sum of the different probabilities or densities of our different components. Okay, so alpha is going to be the mixing weights for each of the different components. P is the probability, the PDF, the density function for each of these different things. Okay. And then Z is going to be, as far as what are the parameters go, it's going to be, Z is going to be a 1 or a 0, indicating whether a value belongs to a certain component or not. And that's what we have here. Okay. So here is the code used to generate um, our points. And so first I'm going to enter all of our parameters here. So I have my mixing proportions in this vector alpha, 50% component 1, 30% component 2, 20% component 3. And then I have the vector for the mean of component 1, the mean of component 2, and the mean of component 3, 0, 0, 4, 4, -4, -4. And then I have the matrices, okay, for each of the components. So, 9009, is this one. The next one is 1.9.91, and then the third matrix there. And then I'm going to gather them all together into just a list. So I have a list of the means and a list of the sigmas. And then to generate my data, okay, I'm going to use the multivariate normal. And with the multivariate normal package, I can generate random multivariate normal values. Okay, so here I'm going to generate 1,000 data points. So the first thing is I'm going to generate a random value between 1, 2, or 3 with probabilities alpha. So I'm going to generate ones with probability 0.5, twos with probability 0.3, and threes with probability 0.2. So that's going to generate a random k. And then once I have the random k, so let's say k gets generated to be number 2, I'm going to say generate using the random multivariate normal function, generate one data point using the mean sub k. So if it's means double square bracket 2, it's going to take mean 2. So it'll say a mean of 4, 4, and the standard deviation sigma 2, which will be, 1.9.9. Okay, right there. And then also just keep track of which component it came from and store that in our X matrix. So X matrix is going to have 3 columns, basically a column for X1, a column for X2, and a column for K, which component it came from. And here, if I plot our resulting data, this is the resulting data of our mixture. They're going to come in completely unlabeled, okay? because remember, this is unsupervised learning, so we don't actually know um, the answers or the classes any of these belong to. But you can kind of eyeball and see the different components. Okay. Um, I I think on the next slide I have them colored in based on the components that they generated from. And so you can see in the center, okay, this kind of uh, cluster one, our first component, is centered at 0, 0, accounts for 50% of our data, centered at 0, 0 with, variance 9, or basically standard deviation 3 in each direction, variance of 9, no covariance. And then our second component is centered at 4, comma 4, and there's high covariance between x1 and x2. And then our third component is centered at -4, -4, and then there's some negative covariance. Okay. So here our values are labeled, and so we can see the components that they came from. But when we observe our data, it comes in like this. And the question is, can we identify, different kind of clusters here? Okay. So Um, when we do this, we might ask a question like, okay, here's a data point right here, okay, at this thing. And let's say we have an idea and say, yeah, there's these different kind of clusters, and maybe we don't fully know, but if I say, okay, what should the assignment of this point be? Okay. Is it coming from the cluster centered at 0, 0, or is it does it belong to cluster one, or does it belong to cluster two centered at 4, comma 4? Right. And so if we look at cluster two, you know, we can cluster two is centers located over here, but we say, yeah, you know what, this point out here is kind of on the edge. So we're not quite sure if it should belong to that or not. Okay. And maybe it should belong to this, um, we're not 100% sure. And so rather than doing a hard assignment like with k-means clustering, where we just say this belongs to the cluster whose centroid is the closest, maybe we can give a probabilistic assignment. Okay. And we could say, you know what, a point right there at the tip of that blue arrow maybe is 50% cluster one and 50% cluster two. Okay. Maybe, or we could adjust it 60% cluster one, 40% cluster two, depending on these kinds of things. And so you can see how understanding the Bayes classifier, because basically the Bayes classifier did something similar, um, would inform how we should classify these things. Okay. So part of the EM algorithm here is going to work a lot like the Bayes classifier. Okay. But with the Bayes classifier, we knew we had estimates for the means and standard deviations of our different components based on our training data. With the EM algorithm, the means and standard deviations are unknown to us. Okay. So, so we want to classify things, okay, or cluster things using the Bayes classifier, but we also need a way to update what our means and standard deviation estimates are. Okay. So, so this slide says, when you're dealing with a point like this, we are going to use a probabilistic assignment. So yeah, rather than strictly assigning a point to one cluster, like in K-means clustering, okay, we're going to use the Bayes classifier to get a probabilistic assignment. And we're going to call this thing the membership weight, okay? So each point is now going to have a vector of membership weights that add up to 1. And then once you have those membership weights, we're going to calculate um, the parameters of each cluster. We're going to calculate what is the mean of each of these clusters and what's the kind of covariance matrix. And we're going to do this by using a weighted mean and weighted variance covariance matrix um, using those membership weights. Okay. And that's going to maximize the likelihood of the different values that are quote unquote assigned to each cluster. And we do this, take this iterative approach, going back and forth between calculating the membership weights and recalculating the parameters. Okay. And so it could be useful to think of the EM algorithm as a blend between k-means clustering and the Bayes classifier. So in k-means clustering, it's iterative. You go back and forth between recalculating centroids and reassigning points. And here we're basically doing the same thing, except um, we're, we reassign points probabilistically, and then we recalculate the centroids or the means using weighted means. And we're also going to recalculate the variance covariance matrix as well. So the membership weights are going to be found using the Bayes classifier. So given um, some point X, okay, all of the parameter values, that is the means and sigma matrices of all of our clusters stored in our big, I guess, vector or object theta. We're going to calculate the weight or the probability that a point belongs to some cluster. So we're going to take the PDF, the likelihood PDF of using the multivariate normal. We're going to ask what's the likelihood of this data given these different parameter values, okay, our current estimates of the mean and standard deviation. The prior is going to be kind of the, how many points do we think belong to cluster A versus cluster B versus cluster C or something. And so that will be our numerator. And then we find the denominator by calculating the numerator for all possible classes and summing them up. So we're going to get our alpha, that is the prior probability, okay, from our previous iteration. And that's going to be basically how many points belong to cluster K. All right, so this will be equal to the proportion of points that are assigned to cluster K. And so we'll do the number of points in cluster 1 divided by the total number of points, or the number of points in cluster 2 or cluster B divided by the total number of points. Okay. However, this number of points isn't an integer because points are probabilistically assigned. So we're not saying, okay, these 5 points were assigned to cluster 1. It's going to be more like we add up the weights. So perhaps, the first point is 90% membership cluster 1, and the second point is 30% membership cluster 1. Okay, so when you add those up, cluster 1 has like 1.2 points, right? 90% plus 30%, 1.2. So we have, the number, quote, number of points, this n sub k is going to be the sum of the different weights. And that's how we get our prior probabilities, okay? The likelihood is just the multivariate normal density function. And so this is the PDF of a multivariate normal distribution. And thankfully, we don't have to work this out. I mean, we could, but we can just use the density function from the multivariate normal package. So we can say, give me the density for the multivariate normal for, whatever our test case point is, our new point, and then given basically the means of all of our the mean of cluster K and the variance matrix of cluster K. So that's how we're going to calculate our membership weights. So we have a way to calculate our likelihood, a way to calculate our prior probabilities. We're going to take the product of those things, calculate it for all of the different classes available, and so then we can get the update all of our membership weights. Okay. So we do that. We update all of the membership weights for every single point and all of the different clusters we have. And once we've done that, then we're going to recalculate basically the centroid of each cluster and the variance of each cluster. So the centroid or the kind of the mean of each cluster will be recalculated using a weighted mean. Okay, so we're going to basically multiply the weight of each point times the values in that point, and we're going to sum this up. Okay, So some of the points might have weights that are close to 1, indicating strong membership to uh, that cluster, and those values will basically get counted fully in there. And other points will have weights that are close to 0, okay? And so those points barely contribute anything towards the sum there, okay? And then we're going to divide by the sum of the weights, which is 1 over n sub k, okay? So, so this will give us the weighted mean of basically the points that belong to cluster K. And we do something similar regarding getting our variance estimates. So, for variance, normally we just do x minus mu times x minus mu transpose. And here we're going to take that x minus mu times x minus mu transpose, but multiply it by a weight. Okay, and then we'll sum them up, and then we'll divide by the sum of the weights as well. Okay, and basically you will implement this algorithm in your homework assignment to do the EM algorithm. Okay, so here our clusters are not labeled. This is how the data come in, and so you have to just kind of start off with some um, initial guesses. Okay, and so here I'm going to just come up with arbitrary values for what the mixing parameters are. So I'm going to just start off with arbitrary guess of 0.3, 0.33, and 0.34. Okay. The true values are what? 0.5, 0.3, and zero point 0.2. And then here I'm going to just start off with 3 random locations or arbitrary locations for where our means are. I've got 0, 0, -9, -9, and 9, comma 9. And then my covariance matrices, I'm just using the identity for all of these things. Okay, so these are all not good. And this would be kind of my initial assignments here. And based on this, using the Bayes classifier, I classify each point and say, does it belong to this cluster, this cluster, or this cluster, or something like that. Okay. Now, and I've colored the dots in accordingly. Okay. Now, there is something a little bit misleading about this graphic is that, these points right along here, they're not, um, they're colored either to be black or green, but the points aren't, remember, we have probabilistic assignments. So these points right here, this point right here is probably like 51% cluster 1 in black and 49% cluster 2 in green. And these points that are green over here are probably 49% cluster 1 and 51% cluster 2 in green. Okay. And so as far as coloring the points go, um, R can only color it one color, so it ends up looking like this. But truly, they actually have probabilistic assignments, and these values that are right along this border are more of a blend of like 51%, 49% versus 49%, 51% between our different things. And same kind of thing there. Okay. But anyway, these are our current assignments. And based on that, we're going to say, okay, recalculate what your estimated mean is and recalculate the estimated variance. Okay. So at the next iteration, we're going to see all of these, the centroids of these things get updated. So as far as the green dots, the centroid will probably move closer to the center of these green dots. This centroid will move closer to the center of the red dots. And then it'll also try to take into account the variance. And so one thing we'll see is like, because there's so much variance with all of these dots in black right here, the variance is the ellipses here that represent the variance is going to get very spread out. So okay, so this is just to kind of say the 51.49%. So at the next iteration, this is the calculation. So this is the updated centroids, and then kind of the ellipses represent the updated sizes of the variance and covariance matrices. Okay. And so we can see, um, things have updated. And so now given these new centroids and variance covariance matrices, we have reassigned or recalculated the membership weights. And so, again, zooming in here, we could see, some of these points are more likely to be in the green cluster. Some of these points are more likely to be in the black cluster. Some of these points are more likely to be in the red cluster, and so on and so forth. And so this is, um, that's what the diagram looks like. Okay. And so at the next iteration, it looks like this. And I just kind of keep running the algorithm iteration after iteration. So here I'm running backwards. So kind of starting here at the next iteration and updating, updating, updating. This is kind of where it ends up after several iterations. Okay. And so kind of our final clusters would look something like this. Okay. We have a point centered, a cluster centered here, cluster centered here, cluster centered here. And using the EM algorithm and the Bayes classifier, we say, all right, these points are very likely to belong to this cluster. These points up here are very likely to belong to that cluster. Okay, we can compare this to the original classes that generated our data. Okay, and again, the label switching issue is a thing. This one happened to get labeled green, and this one happened to get labeled red, whereas in the original data, this was labeled red and this is green. That doesn't matter. It's clustering. There's no actual answers. And you can see, these points down here is a mix between points that belong to this cluster and the center cluster. We have a mix of kind of green dots and black dots here, okay? Whereas in the final assignments, okay, these are colored probabilistically or based on the ones with the highest probabilities. So all of these points colored in red here all have their probabilities are highest for the red cluster, okay? But but they really are a mix, okay? And so probably some of these points are like 70% red, 30% black, or something like that. Okay, so some kind of mix like that. Um, and that's what you have. Okay. And so so that's the EM algorithm. It works on this. And the EM algorithm is able to take into account basically different amounts of variance where k-means clustering is not able to do that. K-means clustering is always going to say points get assigned to the nearest centroid. So if you just say, hey, these are my three centroids, a point like located right here um, would get assigned to the green cluster. Okay. And, when we look at this, we can say, well, this point out here, um, should not get assigned to the green cluster because when we look at the green cluster, there's such high covariance that it is unlikely to produce a value where, x1 and x2 are quite a bit different like this. Okay. So, um, so the EM algorithm is able to kind of take into account the variance and covariance matrices by saying this is going to be unlikely to belong to the green cluster because of the difference in covariance there. Okay. And so the EM algorithm takes that into account and is able to illustrate all of this. All right. So I think that's pretty great. You can try it out with different starting locations. All right. And so here I said, all right, what if I start off with these different starting locations? And after one iteration, so these ones got colored green and these ones got colored red. After one iteration, this is what we have. And then we let it run and uh, it kind of struggles. But I think, let's see, does it eventually get it right? Uh, I think this one, okay. I think eventually, so. just running through a bunch of slides. Oh, it says fast forward to the end and then it runs out. I think eventually, um, sometimes it, based on your starting location, it might struggle and it might not converge. So this one ran a long time and then I don't actually we didn't reach the convergence there. I might have had it in a different slide deck. Okay, oh here I guess I started with different starting locations. So there, and then kind of sliding through this one eventually gets it right. So, um, so like the k-means, clustering, which is iterative, all of these things that are iterative, a lot is conditional on your starting location. And so as you run these things, sometimes you can run into issues where things don't converge because you had a bad starting location or something like that. So, anytime you have an iterative thing, it is generally worthwhile trying different starting locations, different initial values, um, to kind of see where they go and where they converge, or if they converge at all. Okay. But basically, the summary of the EM algorithm here is that, you know, we take time to update our membership weights. These are the missing values because we don't know where things belong. And then missing values in our data. And then once you have kind of guesses for those membership weights, you're going to recalculate the unknown parameters, in our case, the mean and variance. And we use weighted values for the mean and variance there. Okay. So that's the EM algorithm. All right, let me now bring in introduce principal components analysis. So this is another unsupervised learning method, and this we use for dimension reduction. Okay, so in principal components analysis, the idea here is that we want to reduce redundant variables. Okay, so you might have a data set with a whole bunch of variables, and a lot of times your variables are going to be correlated. And what PCA will do is it will transform the variables into uncorrelated variables. Okay, and the goal here is dimension reduction. Okay. And so, if we can take advantage of the fact that a lot of these variables are correlated, can we reduce the number of variables and still kind of capture, convey the important aspects or traits that exist in the data? Okay. So an example is like, if you search for a house or an apartment, there are like a ton of variables. Okay. You have like the square footage and the number of bedrooms, number of bathrooms, maybe the lot size, other attributes like if there's a pool or the roof and um, you know, uh, the quality of the kitchens and stuff. Also, you have location information like the zip code and the school rating and median price of the homes in the surrounding area and things like that. And I would say a lot of these things can be reduced to just all of these different variables can be reduced down to just a few factors. One is going to be the size, okay? And basically square footage, number of bedrooms, bathrooms, these all are very highly correlated. They usually go up or down together. It's rare to find a place with a whole bunch of bedrooms and hardly any bathrooms, or vice versa. Like you're not going to find a place with five bathrooms and one bedroom or something like that. Okay. And um, so you have that. And then a lot of times the quality of the place goes together. And then also the location. And so, if you think about if you're like searching for an apartment or a house or something, um, on the search results page, what is the information that is shown on the search results. Because search results basically they want to just give you like the they want to convey as many search results as possible and these essential information that you need to know. And so you're going to get things like, okay, the price, a picture, because the picture is going to convey things like the quality. And then it'll also probably have something about like square footage and number of bedrooms and bathrooms or something like that. Okay. And it's not going to have all of these other variables about lot size or things like that. Okay. Um, Other examples of dimension reduction are that are useful are things like GPA, all right? For better or worse, we have a GPA that kind of tries to reduce your entire academic performance down to a single number. Okay, by definition, it is very reductive. And so, admission decisions for universities and grad school and stuff probably is not going to be based on GPA alone, but it can be a useful thing, especially if you have to compare a whole bunch of people at once, right? SAT and GRE scores, again, this tries to boil down some complex notion of, I don't know, intelligence or test taking ability or something down to just a couple of numbers, okay? Um, in the financial world, you have things like a credit score, and that tries to boil down, something complicated like how likely somebody is to repay a loan down to a single number. Okay. In sports, you have uh, things like the passer rating. This is a rating of like a quarterback, quarterbacks like passing performance, like how many throws did they attempt, how many throws were completed and or passes were completed, how many interceptions and things like that. Um, and you get a score there. Other examples like in there's certain sporting events like in the Olympics, you have like decathlon, heptathlon, and you have scores on these individual components like the runs and the hurdles and the jumps and things like that. And it has to be combined to a single score so that you can rank people from, gold medal, gold, silver, bronze, and things like that. Okay. So, another way to think about dimension reduction is you can think of like an object casting a shadow. Okay. So, uh, all of our objects that we interact with exist in three dimensions. But if you take it outside and the sun is shining, that object is going to cast a shadow. All right. And that shadow is basically a two-dimensional projection of the object. And depending on how the shadow is projected, the shadow might resemble the original object or not. Okay. And so if you think about, um, I don't know, like a pen, okay, in one orientation, you can see, let me see, right? So here I have a pen, okay? And when I hold it like this, you can tell that it's a pen. But if I hold it like this and you can barely see it, and it's just like this little circle and a point, and this is orientation, it's a little bit difficult to tell exactly what it is, right? And if it's casting a shadow and the pen is oriented in such a way that the shadow that it casts is basically a tiny little circle, it's going to be difficult to tell what that is. Okay. Versus if you hold it sideways, you can tell the difference between, oh, that's going to be a pen or a battery or a highlighter or a marker. Oriented in another way, they all just like look like circles. Okay. And they're difficult. And so what we want to do is for our data that exists in some higher dimension, we want to cast it down or project it down to a lower number of dimensions, yet we still want that lower number of dimensions to resemble our original data. Okay. And so when we say we want a lower dimensional projection that resembles the original data, we're saying that we want a projection that captures as much of the variance that exists in the original high dimensional data. And when you do, but when you reduce the number of dimensions, you are going to lose some information. Okay, we're not going to be able to capture all of the variance that exists in the original data, but we want to try to maximize the amount of variation that we are able to capture. Okay, and so we're going to search for a lower dimensional projection that maximizes the variance in the resulting projected space. Okay, so what we're going to do is we're going to define these basic, I guess what we call loading vectors, okay, which are basically just weights. We're going to find a linear combination of the original variables, like a recipe of like how much of each of the original variables to mix to get these resulting kind of principal component, which project our data. So we're going to say our original data exists in m dimensions. Okay. And so when we're talking about the nth observation in that original data, that nth observation is going to be a vector of length m. And what we want to do is we want to project the data down to d dimensions. Okay. So, we can say we're going to start off with variables in 3 dimensions and we want to project it down to 2 dimensions. Okay. So our y, each observation in y has 3 components. Okay. Values in 3 dimensions. And what we're going to do is after we project it down, okay, the resulting projected data will exist only in 2 dimensions. So x will have basically a length of 2. And so what PCA will do is it's going to define 2 vectors, okay? And each of those vectors will be length 3, okay? It's going to define d vectors. Each of them has a length of m. And when you multiply that weighted vector W times the original data, it's going to give you your projected data. So if you take that vector W and multiply it by the 3D data, it's going to give you back, uh, you have 2 of these vectors and you'll get each a component in X. Okay. So each of the elements in X is going to be the projected data. These are just linear combinations of the values in Y, okay? And each of which is weighted by the values in W, okay? So if we want to project from 3 dimensions down to 2 dimensions, we would have two of these projected vectors, each of length 3. We're going to have a W1 and a W2, and when you multiply your observation y by W1, you're going to get the first component in X. And then when you multiply that observation by W2, you'll get the second component. Okay. And what we want to do is we want to choose our W's so that the variance in the projected space is maximized. Okay. So that first vector, W1, is going to be the set of weights so that the variance in the projected values is as high as possible. Okay. The second vector, W2, is going to maximize the variance in X2, but it has to be orthogonal to W1. So that is W1 transpose W2 is going to be equal to 0. And if you have a third weight vector or something, it'll maximize the variance, but it has to be orthogonal to all of the previous vectors and so on. There's a typo here. It should be, in general, Wi transpose Wj, not Wi again, but Wj is equal to 0 for all I not equal to j. And then to avoid having infinitely many solutions, we're going to restrict the length of each vector to be 1. Okay, so Wi transpose Wi is going to have a length of 1. And so what we're going to do is we're going to derive the vector W1 so that the variance in X1 is maximized. And what we're going to do to kind of simplify our calculations in our work is we're going to start by centering the original data. So we're going to just subtract the column mean from each column in Y so that the mean of Y is equal to 0. So we're going to center our data. So we're just shifting our data down, up or down, so that it's centered at 0. Okay. And then we'll just work with kind of one of our weight vectors. Okay. And so what this is going to do is it's going to take each observation y and project it down to just one scalar value x. Okay, so just we're going to take one vector w, multiply by y, and we'll scale it down. And basically, w is going to be like, how should we add up the values in y? So, at the simplest, you can just say like take the different values of y and add them together. And that's basically what we do with like SAT scores. You have like a verbal score and a math score. And um, one form of dimension reduction is just add the scores together, right? Your total score is your verbal plus your math. And that's basically dimension reduction. You're going from two individual components, verbal and math, and then you're saying, let's just add them together to get our total or something like that. Okay. Um, and uh, and that will reduce the number of dimensions. But here we're going to try to say like, okay, is there a way to combine them in such a way that maximizes um, the variation in the resulting projection? Okay, and so what is the variance of the resulting projection? Okay, we're going to do the definition of the variance is going to be x minus x bar, the average square distance, so x minus x bar squared, 1 over n. This is kind of our, if we treat this as a population, okay, without Bessel's correction of n minus 1. And we're going to say, okay, well, let's try to maximize this. Okay. So one thing is that because we said the mean of y is equal to 0, that means the mean of x is also going to be 0. So if I say, all right, well, what is the mean of x? The mean of x is going to be basically the sum of x's over n. Each x is w transpose times y. And w is the same for all of these things. So I can pull it out. Now I have the sum of all of my y's. And earlier we established that we have centered our y matrix so that the sum of our y's is basically going to just be the 0 vector. And so I can do, w times the 0 vector, and that's going to just be 0. Okay, so the mean of x is going to be 0. And so our variance expression, we can simplify. We can say, okay, our variance is the difference between x minus the mean of x squared. And so here, the mean of x is 0. Okay, so now I have, it's basically this sum of all of my x's here. I'm going to replace x with w transpose y. And here I'm going to square this. And so when I do this, I can expand this out to w transpose y transpose w. Okay, and we have this for each observation, y sub n, and we're going to add this up across all of these things. And because w is going to be the same for all of our observations, I can pull that out here. Okay, so I'm going to have w transpose times, and here I have the sum of basically y transpose, okay, times w, right? And this is going to be an m by m matrix, and each value is going to be m by 1, and w transpose is 1 by m, and so the entire product of this thing is going to be a 1 by 1 scalar. So, and what I want to do is I want to find the w that's going to maximize the resulting expression, okay? This component here in the center, this m by m matrix, this is just the definition of the covariance matrix of y, right? So the definition of the covariance matrix is, y minus the mean times y minus the mean transpose. Okay, this is the definition of covariance. And because the mean of y is 0, all right, it can it reduces down to this, which is exactly what we have here. Okay, so my variance is going to be w transpose times the covariance matrix of w here. And I want to maximize this thing. Okay, well, I can't just, you know, I need to apply a constraint. Okay, otherwise I could just pick w to be like infinity, and that will maximize their value. So we're applying the constraint that w transpose w is equal to 1. Okay. So we want to maximize the variance subject to the constraint that w transpose w is equal to 1, so we don't have something unbounded here. And anytime you want to maximize something subject to a constraint, one of the techniques you can use is a Lagrange multiplier. So we're going to say L is equal to the thing that we want to maximize, W transpose CW, minus, and then we're going to have lambda times W transpose W minus 1. Okay. This part is equal to 0. This is the constraint. And then, so to maximize this, we will take the derivative of this and set it equal to 0. So I'm going to get 2 times CW minus 2 times lambda W. This is just taking gradients or derivatives with respect to vectors. We set that equal to 0. And this gets me in the form covariance matrix C times W is equal to some scalar lambda times W. All right, so here I have a matrix times a vector is equal to a scalar times a vector, and we want to find, and the solution to this is going to be the W that, uh, you know, is where derivative is equal to 0. Okay, so whenever you have it in this form, matrix times a vector is equal to a scalar times a vector. The solution to that kind of problem is that W is going to be an eigenvector of C, and lambda, the corresponding lambda will be the eigenvalue. Okay. And so the resulting eigenvalue eigenvector pair with the highest eigenvalue will be the projection with the highest variance. And then the second highest eigenvalue will correspond to, say, W2 and so on and so forth. Okay. So this is how we would go about performing principal components analysis to go from M dimensions down to D dimensions. Is first we have to center all of our data, and then we're going to compute the covariance matrix C, and then you're going to find all of the eigenvector eigenvalue pairs of that covariance matrix. And then from there, you can just select the eigenvectors of the highest with the highest eigenvalues, and then and then to kind of project your data. Now that you have the W's that you've chosen, you multiply original data Y times W to get your projected data X. So let me show an example here. So I'm going to load up the multivariate normal, and I'm going to just generate some values here. Okay. So here I'm generating some 15 points here. This is my covariance matrix. And if I plot this, this is just what the kind of my random generated data looks like, okay, in 2 dimensions here. And so what I want to do is I want to find a basically a one-dimensional projection of this, okay? I want to reduce this. And so I'm going to find the covariance matrix. And first I'm going to center my data, okay? And so here X-centered is going to basically center my data so that if I calculate the column means of my center data, my column means are all 0 now, okay? And then I can just say, what is the covariance matrix of this? All right, here's the covariance matrix of my center data. And then I'm going to ask for the eigenvalues, okay? Or the eigenvectors. So this is when you call eigen on the covariance matrix of this, you get 2 eigenvalues and 2 eigenvectors in columns here. So we're going to take the vectors and the values, and we get our eigenvectors here. And so if I keep both eigenvectors, I can get a projection of this. And I'm going to just multiply my center data times Q. And and let me show the plot here. All right. Hmm. So basically what this does is it's just a rotation. It's going to be a rotation of the data. All right. So right now, um, our values exist in our two variables, V1 and V2. And basically I'm going to rotate the data. And so this kind of does it does like a full spin around, okay? And you can see kind of like this component, these two dots here, end up kind of spinning around over to there, okay? But it's just a rotation. I wonder if I can, maybe I can multiply, like, let me see if I can multiply everything by -1 so it doesn't look as obvious. All right, here, let me just delete this. So the signs, all right, so here maybe it's a little more clear that it's just a rotation. Okay, so I just multiplied it by -1. Okay. But here we're just taking the data, the original data, and then we're just doing a rotation. Okay. And so now I still have two components. Okay. Principal component one and principal component two. And if I keep only the first principal component, and I plot this, and let me see PC1. Um, okay, let me just do ASX is going to be, let me just do it 0 here. 10 data must return. Okay, so here's kind of our original data. I'm rotating it. And then the next part is I'm going to just get rid of one of the variables. And so all of these dots are just going to collapse onto uh, onto the I guess x-axis. So these two dots will get kind of collapse onto there. These dots will collapse down to here. All of these dots, I don't know if you can see, we're just reducing, we're just kind of collapsing them onto the x-axis here. So here's the original data. We're rotating it to maximize the variance in one direction, and then we're going to just kind of collapse it. So it's just kind of um, original data, a rotation that maximizes the variance in one direction, and then we've collapsed it down to here. Okay. And then what I can do is then I can take that and try to turn it back into two-dimensional data. And so when I do that, again, here, let me see if I can. This takes our data and then rotates it back. Okay. So here's the original data. We've rotated it, collapsed it down, and then now we're rotating it back. Okay. And so if you compare the original to this, basically we've reduced it down to a one-dimensional setting. Okay. But the idea is that it's supposed to still try to kind of resemble the original. So if this is the original, what we've done is we've rotated it, reduced the number of dimensions down to one, and then we're trying to kind of recreate the original data. So yes, we absolutely lose some information because over here we had our data existing in two dimensions. Okay. But if you look at this and you look at this, there is similarity in the structure, right? And that's basically what we're doing. You can run principal components analysis using either PrinComp or PRComp in R, and this will do very kind of similar things. Because these are rotations, um, sometimes you end up getting like negative versions, and so here I put in like negative Q and things like that. But basically the signs, it's the maximum variation, like it might be pointing right to left or it might be pointing the other way. And so the signs on these rotations are less important. But the idea is you've taken kind of your original data, you're rotating it to kind of maximize the variance in one direction. And then once you have it maximized, you can get rid of one of the other dimensions and you're only losing a little bit of information. Okay. Versus um, if I uh, just completely got rid of, if I got rid of X1 or X2 here, I think we would be losing a lot more information. Okay. So this one kind of keeps a the sorting of the order. If we go from like the maximum is over here, um, it preserves a lot of that information. Okay. And then so even after reducing it down to one dimensions, if you try to kind of plot it back, it preserves kind of that information there. There's another let me just show a diagram here. Oops. Okay. So here's our data set, and then when you reduce it down, you get down to one principal component here. And so the original data in X and Y, it's kind of split, spread out over X and spread out over Y. And then over here, we've maximized the amount of variance on principal component one. And then principal component two has very little variance. And so we can kind of throw it away and we don't lose that much information. Here is a three-dimensional example. Okay. And so, when it's rotating in 3D, you can kind of see there's this structure of having, three different clusters here. Okay. But if you just say, hey, let's look at only X, you don't really, or look at only Y or look at only Z, okay, our data in just one of these directions, it's hard to see kind of the structure of that there's three clusters here. So when we do a principal components analysis, it's going to try to find a rotation so that principal component one maximizes the amount of variance. And so when we do the principal components analysis, it rotates the data in such a way that um, now we have along principal component one, we can see that there are three clusters. Okay. Principal component two and three, now we've lost, it maximizes the amount of variation there, and principal component three has the kind of the least amount of variation there. But so we can kind of throw away principal component three, and we don't feel like we're losing a ton of the original information from the original diagram. Okay. We have a lot of the structure, okay, a lot of the structure of the original um, data in three dimensions shown here by saying that we can still kind of preserve the structure of there being three clusters here. Okay, so this is an overview of how principal components analysis works. There's just some more examples of this, but basically this is an illustration of how PCA can preserve the structure of the original data in such a way that you can kind of get rid of some of these, like the third dimension here, and still preserve a lot of the original structure without losing too much information. All right. That's all I've got for today. So we'll go ahead and just wrap things up a little bit early. And good luck as you start studying for the final exam. And yeah, we'll see you guys next week. I'll just kind of have a fun lecture planned for that one, a short one there, and then we'll see you guys on Thursday for the final. All right, thank you. All right, have a great day.